Alright, welcome back. Math 1910. We are wrapping up Chapter 1 today. We're in Section 5 and we're going to talk about infinite limits. Okay? What does that really mean? Alright, we're looking at kind of what the end behavior of the function is going to be as, x approaches a specific value. So as x approaches 1, alright, is it going to be going from negative infinity to positive infinity, or we're going to still deal with one-sided limits where, as x approaches 1 from the left. Is it increasing or decreasing without bounds? So is it going to negative infinity or positive infinity? All right, and then we're going to calculate, where vertical asymptotes occur in a function. Okay, so let's start with an example here. We're taking a look at this function here that is 3 divided by x minus 2. So if we were to graph this in our calculator, now your calculator, remember, is not going to show the vertical line. We did extensive work on this in pre-calc 2 when we did a lot of trig functions and drew the vertical asymptotes for tangent and cotangent and those sort of things, and secant and cosecant as well. Okay, so we should understand what an asymptote is going to be. All right, so let's talk about what's going on. So if we take a look, if we approach x equals 2 from the left-hand side and x equals 2 from the right-hand side. So first, let's say we're going to approach 2 from the left-hand side. So we're only looking at the graph on the left-hand side of 2. Where is that graph going as it goes from left to right? The graph is going to negative infinity. It's decreasing without bound. That's kind of how we define this as being negative infinity. Okay? If we look at the graph, okay, on the right-hand side, so as we're approaching 2 from the right, so we're going right to left now, and if we were a particle on that graph, we can see that the graph, as it gets closer and closer and closer, arbitrarily close to 2, it's shooting straight up. It's increasing without bound, so we say that that's approaching positive infinity. Okay, and if we do the, what we did in section 2, where we use like a table approach, we can see as we get closer and closer to 2 from the left, it's going to negative 3,000, negative 300, negative 3,000. It's growing substantially, right? And as we go to 2 from the right, it's growing substantially as well. So we can see that it's increasing and decreasing without bound. So what we're talking about is what's the behavior of the graph at that specific x value. So in this case, what's going on at x equals 2. So we can write it as the limit of 3 over x minus 2 as x approaches 2 from the left, right? That's that superscript negative. That's 2 from the left, is negative infinity. And then we can write the other half, right? The limit as of 3 over x minus 2 as x approaches 2 from the right goes to infinity, right? It increases without bound. So there's how we're going to denote those, okay? Limits at infinity and those sort of things. All right, so we're going to be using infinity and negative infinity, all right, to relatively talk about increasing without bound and decreasing without bound. Remember, infinity does not represent a specific number. It just means that it continually goes on and on and on in that direction without bound. So we can say that a limit increases or decreases without bound. We call those infinite limits. Okay, so at that specific x value, if we are increasing or decreasing without bound, we have an infinite limit. Okay, so here's the definitions. All right, so I'm going to just kind of read through these, make sure that you have them in your notes. All right, so if we go through this, okay, it says let f be a function that is defined at every real number in some open interval containing c, except possibly at c itself. So we can say the limit of f of x as x approaches c is infinity. Now this is where we're defining the limit is infinity, because the left-hand side and the right-hand side both have to agree. Okay, so we're going back to our delta epsilon definition here as well. All right, so that means for each m greater than 0, okay, there exists a delta greater than 0 such that f of x is greater than m whenever 0 is less than the absolute value of x minus c, which is less than delta. Okay, so what is all that concluding? Okay, what's our delta? This isn't changed. This has not changed. Okay, m is our value, just like our f of c sort of type value. So delta is still our change in C, right? Delta is that amount, so we can go C plus delta, C minus delta, and we'll still get ebb for each one, whatever that value appears to be for that specific problem. Okay, so if they're both going to the same thing, but right, but C does not exist, right? Because C does not exist because there's an asymptote there. That's where we're going to apply this. Okay, so we can define the limit from the left and the limit from the right. This will make more sense kind of as we do a few more problems. Okay, but this is still stemming back to our delta epsilon stuff that we did earlier in this chapter. Okay, so let's take a look here. We want to determine the limit of each function shown in each of these two figures as x approaches 1 from the left and from the right. All right, so when we take these are going to be two separate problems here. So you can draw it down on the next slide. Okay, so when we look at this, all right, if you graph this, we can see clearly in the function, right? If we have x equals 1, what's going to happen? The denominator is going to go to 0. But we have to determine, okay, graphically helps us. Is there a definite limit, right? Or is there a left-hand limit or right-hand limit, and what's really going on here? So, how do we conclude this? Well, if we approach 1 from the left, and we take a look at the graph, as x approaches 1 from the left of 1 over x minus 1 quantity squared, we can see that it goes upward unbound to positive infinity. If we approach 1 from the right, all right, moving right to left, we can see that the graph also approaches infinity. So the left-hand limit and the right-hand limit agree. They're both going unbound, they're increasing unbound, both going to infinity. So we can conclude that the limit of 1 over x minus 1 quantity squared as x approaches 1 is infinity, because the left-hand limit and the right-hand limit both agree in this problem. Okay? Okay, so also, what's really happening, right, is we're creating a really, really, really large denominator there if we substitute in. Or, no, I'm sorry, not a large positive number. Okay? So that's why we're going to go to infinity when we substitute that in. Alright, so if we take a look at the other problem, okay, well, we had this problem. The graph's gonna, show up on the next slide. It didn't show up on this side. So I'm going to talk about it on this. So as we approach this one from the left and from the right, we can see if we approach this function here from the left-hand side, as we're approaching 1, we can see that this graph increases without bound. So we know that the limit as x approaches infinity from the left is going to be positive infinity. That's not what's shown on the screen. I'm just referencing the graph here. Okay? What's shown on the screen is the limit as x approaches 1 from the right. So if we approach x equals 1 from the right, we can see that the graph goes down to negative infinity. Okay? Now, the left-hand limit and the right-hand limit do not agree. So there is not a limit for this problem, but there is a left-hand limit and there is a right-hand limit. Remember, the limits have to agree for the limit to exist. So in this case, there's a left-hand limit, which is infinity. There's a right-hand limit, which is negative infinity. There's not a limit because the left-hand limit and the right-hand limit don't agree. Okay? So just making sure that we understand that. All right, the next thing we want to talk about is vertical asymptotes. We should remember from pre-calc 2, right? A vertical asymptote occurs anytime that we are going to have some sort of division by 0, okay? But there is another stipulation, right? Because sometimes division by 0 just constitutes a hole in the graph, not necessarily an asymptote. So we have to be able to define what's going to be the asymptote, okay? So as you get arbitrarily close to this vertical line, all right, so what does that really mean? So let's look at the graph on the left here. We have 1 over 2 times x plus 1. Well, we know that if we plug in -1 or substitute -1 in for x, well, all right, we get division by 0. So we want to look, all right, as we arbitrarily get close to -1 from the left-hand side and from the right-hand side, what's going on? Well, we can conclude that since from the left-hand side, it's decreasing without bound, and from the right-hand side, it's increasing without bound. We're going to conclude that we have a vertical asymptote here. We're going to say that it gets arbitrarily close, infinitely close to -1, but can never be -1. Okay, let's look at the second graph there. We have x squared plus 1 divided by x squared minus 1. All right, and we're going to learn how to break this up and see where there's two vertical asymptotes and how that occurs. All right, but if you were to graph this in your calculator, you would see that going from, there's different limits here, right? We got to approach -1 and 1 because that's where we can get zeros. Okay, when the denominator is 0, that's what we're going to look for vertical asymptotes. So as we approach -1 from the left, it goes to positive infinity. As we approach -1 from the right, it goes to negative infinity. So we can conclude we're going to get a vertical asymptote there. And then on the other point, as we approach 1 from the left, it goes to negative infinity. As we approach 1 from the right, okay, we're going to go to positive infinity. So we can see that the end behavior, one's going to negative infinity, one's going to positive infinity, so we're going to have a vertical asymptote there. Okay, here's the definition of a vertical asymptote. Okay, if f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph. Okay, it's very important that we have that issue. It's got to be able to approach that so we don't have the holes in the graph like we did in like section 2 when we did the first part of understanding limits in this chapter. So very important note on this is the asymptote occurs when the denominator is 0, not when the numerator is 0. Okay, so there's some theorems that we have that help define this, and this is what's really going to help you define, your vertical asymptotes. All right, so if I'm gonna read through this theorem here, and then we're gonna apply in a few examples here. So we have let f and g be continuous on an open interval containing c. Okay, so if f of c cannot be 0, right, and g of c is 0, and there exists an open interval containing c such that g of x cannot be 0 for all x not equal to c in the interval, then the graph of the function h of x is f of x over g of x has a vertical asymptote at x equals c. All right, what does all that really mean? We have to see, as long as f of c is not 0. So that means what? The numerator cannot be 0 here for this theorem to work. The numerator has to be a value, whether it's positive or negative. And then what it's saying is the denominator, okay, wherever the denominator is 0, okay, we're going to have a vertical asymptote at c. So if the denominator goes to 0 at c, we'll have a vertical asymptote at c. But the key is the numerator here has to be positive. All right, so we're going to find all the vertical asymptotes of each one of these functions here. All right, so we're going to do 3 different examples as we go through this. So the first one is f of x equals 1 over 2 times x plus 1. We already kind of took a look at this one earlier. Okay, so the numerator is not going to 0. Good, that's good. All right, the numerator is 1. Okay, and the denominator goes to 0 when x equals -1. Right? You can either, if you remember finding zeros before in Algebra 2 or pre-calc, right? You take that denominator, set it equal to 0, solve for x. Well, in this scenario, we can visually see that if x is -1, all right, the denominator goes to 0. So we can conclude there that when x equals -1, okay, and we are increasing and decreasing without bound as we approach 1 from the right and the left-hand sides, all right, we can conclude that there's a vertical asymptote at x equals c, and in this case, c is -1. Okay, and we're using that theorem. So the numerator is 0, all right, and then we got to look at, we are increasing without bound as we approach that point. We're going to negative infinity and we're going to positive infinity. Just depends on which side we're approaching there. Okay, so let's take a look at this example now. This is the second example. We have f of x equals x squared plus 1 divided by x squared minus 1. What you need to make sure that you understand to do is to factor that denominator. All right, that's the difference of two squares, so you should get x minus 1 times x plus 1 in the denominator. So we can note that what happens? What values make the denominator go to 0? A value of -1 and a value of 1 make the denominator go to 0. So this is where we are getting two different asymptotes potentially. But remember, the numerator has to what? Be not 0. So if we plug in -1 or +1 into the numerator does not go to 0. The numerator is going to be what? No matter what, the numerator is always going to be 2 there. Okay, so if we do that, we can apply theorem 1.4. The numerator is not 0, okay, and we can conclude that we have two vertical asymptotes as shown. Okay, and you can graph this and conclude it as well. Okay, we're increasing or decreasing without bound around those. All right, let's look at the third one here. We've got cotangent of x equals cosine of x over sine of x, right? Remember rewriting that from pre-calc 2. So what's going to happen here? Every single time sine of x is 0, we will have an asymptote. So we have to remember, when does sine go to 0? Sine goes to 0, at pi, 2 pi, 3 pi, 4 pi, right? Just going on and on around the circle. So that's when sine goes to 0. Okay? And then, so we can conclude that we have asymptotes when sine is 0. Now the important question you might ask, well, you're like, well, hey, the denominator isn't always not 0, right? Because cosine can go to 0 at pi over 2, 3 pi over 2, so on and so forth, 5 pi over 2, 7 pi. But what's really happening there, okay, is it the numerator has to be non-zero when the denominator is 0. So cosine will never be 0 at the same time sine is 0. So that's why this theorem works, okay? So sine is 0 at 0, but cosine of 0 is 1. So the numerator is non-zero when the denominator is 0. So that's why this works, and we can apply this and say that there are vertical asymptotes every single time that sine is 0, because sine and cosine will never be 0 at the same time. Okay, so very important that we apply that when we're looking at this, okay? So we have infinite amount of vertical asymptotes here, and the asymptotes occur at x equals n pi, right? Because we said sine goes to 0 at 0, right? So n equals 0, n equals 1, so pi, then 2 pi, 3 pi, 4 pi. So we have to account for every single one of those. So sine is going to have infinite amount of asymptotes there. But the asymptote, remember, just because we're focusing on sine, it's about cotangents, asymptotes, okay? Cotangents, asymptotes are happening when sine is going to 0, okay? So make sure that we understand that piece. All right, so just properties of infinite limits. All right, this is no different than when we did limits, before. We had sum or differences, okay? So if f of x is going to infinity and g of x is going to infinity, we can conclude that their sum is going to infinity as well, okay? Same with their product. If the limit of f of x is going to infinity, the limit of g of x is going to infinity, their product will also go to infinity. And you can see it would be the same with negative infinity. And the quotient, right? Here's the quotient one we got to pay attention to, okay? Is if we have g of x over f of x and x is going to c, all right, we will get 0, okay? So we just got to be important and understand. We're going to apply these properties in the next couple of examples here so that they will make sense to you, okay? So this theorem is only implied because we're looking at and we are defining up above the limit of f of x as x approaches c is said to be infinity, and the limit, okay, of g of x as x approaches c is L. Okay, so what are we really saying? Well, we're saying infinity plus L is an infinity, infinity minus L is infinity. We're also saying that infinity times L is infinity, and negative infinity times L is negative infinity. And then we're saying what's happening. So that third one, the quotient one, we have limit over infinity. So when we get a really, really, really large denominator, we go to 0. Does that make sense? So if you start comparing values like 1 over 10 to 1 over 100 to 1 over 1,000 to 1 over 10,000 to 1 over 100,000, you will be getting closer and closer and closer to infinity. or not to infinity, I'm sorry, I misspoke there, closer and closer and closer to 0. So the larger the denominator, okay, when we have the quotient, we're going to say that the limit goes to 0. And that's really what's happening there, right? We have some sort of limit divided by infinity. Anything over infinity is always going to be going to 0, unless it's infinity over infinity. But any other numerical value over infinity is going to be going to 0 for us. Okay, so let's determine some examples here. So if we have this function here, the limit of 1 plus 1 over x squared as x approaches 0, we can use the properties we just learned. All right, we know that the limit of 1 as x approaches 0 is 1, and we know that the limit of 1 over x squared goes to infinity. How do we know that? Because it's 1 over an extremely large value, right? 1 over extremely large value. So 1 over, I'm sorry, very small value. We know that, sorry, I misspoke. I'm getting ahead of myself on the examples here. We know that we have 1 over x squared, so it's 1 over 0. We know that, what does that mean? That we have a graph with a unbound. So we know that anything over 0 is going to go to infinity in this scenario. So what can we conclude? We have 1 plus infinity. We can conclude that the limit is infinity. Okay? So when we have 1 over infinity, just to reiterate so we don't get confused here, when we have 1 over infinity, we go to 0. When we have 1 over 0, we go to infinity. Alright, so that's really kind of the difference in understanding those different limits here. So let's take a look at this example here. We have the function, right, is x squared plus 1 over cotangent of pi x. And we're going to take a look as x approaches 1 from the left-hand side. Okay, so we're going to break this into its two pieces here. So as if we substitute in 1 for x squared, right, we're going to get 1 squared plus 1, and that's 2. So the numerator is going to go to 2. The denominator, okay, as x approaches 1, we're going to substitute that in. So we're going to get cotangent of pi. So what does that really mean for us? Remember, cotangent, okay, is cosine over sine. So we're going to have cosine of pi over sine of pi. Well, sine of pi is 0. So we have something over 0. But remember, how do we know it's negative? Because cosine of pi is -1. So since we have -1 over 0, the limit as x approaches 1 from the left will become negative infinity. So hopefully that makes sense, right? We have a -1 over 0, so we're going to negative infinity when we work through this. Okay, and you guys make sure you might have to watch this part a couple times and then work on these on your homework. So you really need to understand, you know, being able to determine those limits. Okay, so now we have what? 2 over negative infinity, right? Because 2 is the limit of the numerator, and negative infinity is the limit of the denominator. So we have 2 over negative infinity. So we have 2 over a really large number. All right, so it goes to 0. So that was like the third property from the previous slide. Okay, and let's look at another example here. We have the limit as x approaches 0 from the right of 3 cotangent of x. All right, so we can separate this into its product, right? So we know the limit of 3 as x approaches 0 from the right is 3, right? It's a constant one. And then we have to take a look at the limit as x approaches 0 from the right of cotangent of x. Once again, we're using cotangent, but we have to know that cotangent is cosine over sine, right? So it's cosine of 0 over sine of 0. Well, cosine of 0 is 1. Sine of 0 is 0. We have 1 over 0, so it's positive 1 over 0. The limit is infinity. So anytime we have 1 over 0, our limit's going to be infinity. Okay, so now we go back to the original piece. So we know we're going to take 3 times infinity, so we're going to get infinity. So the limit of 3 cotangent of x as x approaches 0 from the right is infinity. And let's go ahead and do one more example here. So last example, if we have the function x squared plus 1 over x, and we're taking the limit as x approaches 0 from the left, okay, we're going to break it into its two parts. We're going to do a sum one, right? So we know the limit of x squared as x approaches 0 from the left is 0, right? 0 squared is 0. And then we have the limit as x approaches 0 from the left of 1 over x. We end up getting what? 1 over x, so it's 1 over 0. However, when you graph this, and it's very important, because even though it's a positive 1 in the numerator and it's 0 in the denominator, how do we get negative infinity? You need to graph this function. If you look at the graph of 1 over x, and it's important, as x approaches 0 from the left, if it was as x approaches 0 from the right, we'd be at positive infinity. But you have to look at as x approaches 0 from the left and graph 1 over x on your calculator. Where is it going to? It's going to negative infinity. So you really need to make sure that you understand what the parent function of 1 over x looks like. So now we have 0 plus negative infinity. So now the limit of x squared plus 1 over x as x approaches 0 from the left goes to negative infinity. So we're substituting in those two values that we just found. Okay, I'm going to try and put some more notes for this online. As usual, make sure that you ask me questions or email me or see if we need to Zoom for those of you guys doing this at home. Everybody else, I'll see you in class and have a great day.